for inviting me to speak here. It's been a very exciting week for me, not least because the mathematics here is very interesting, but also because yesterday I officially submitted my PhD thesis. Oh, congratulations. Yeah, but I would like to tell you about that research that I just submitted. And to set the stage, I want to introduce a little bit of notation. So I'll be doing some CM theory. So I'll be using two negative co-prime discriminants D1 and D2, and I use them to define two imaginary quadratic fields K1 and K2. And they naturally fit into this bi-quadratic field L, and then I get this real quadratic field F in the middle. I've summarized the picture also here on this board in case you want to memorize it. And then you also have this character chi here. So this, because I assume these two discriminants to be co-prime, this extension is actually unramified at all finite places. So it induces the character of the narrow class group of F. But its the description is very simple. It just takes a prime ideal and it records its splitting behavior in this extension L over F. Now, I want to introduce a tiny bit more of notation because I'll be talking about the result by Gross and Zagier from the 1980s that I'm sure many of you know. But to state it, I need this function rho of I, which takes a function, which takes an ideal of F, and it outputs the number of ideals of L above it, whose norm is equal to I. This slightly more refined notion, SP of I, which I call the special prime of an ideal, which is not non-standard the terminology, but it makes things easier to talk about it. And I define it to be L when it's a unique prime that is inert in L over F, but which divides I an odd number of times, and it's one if I have more than one such prime or just no such prime. And the way these two notions interact is if I have at least one of such a special prime, then it's actually an obstruction to the ideal being a norm, because if it's like inert in this extension, then if I take the norm, I get the ideal twice. I can never get it to an odd power. Now, to state the Gross-Zagier formula as they proved in the 1980s is a different one from the more famous one. I have many formulas. I take an elliptic curve with Cm by, let's say, a maximal order inside of the field K. And then by Cm theory, we know that these J invariants, they live in these Hilbert class fields. And this week has all been about the field, that's generated by a function like this. But it turns out that these numbers themselves are actually quite interesting to study. And in fact, I proved the following quite fascinating formula, which, okay, it looks a bit messy, but let me explain what's going on here. On the left-hand side, I have the logarithm of the norm of the difference between these two singular moduli. So this is just an algebraic number, so it becomes an integer. And on the right-hand side, I have this sort of ugly-looking explicit formula, but I would like to draw your attention to like almost all parts of this. The first is index set of all the totally positive elements in the inverse difference of trace 1, the inverse difference of the field F, which is in fact a finite set, and I'm sure many of you have seen before. And what we have here is this final term is the logarithm of the norm of the special prime. So really what this formula is like a prime factorization of this number, for which each element mu in this ideal, it contributes some prime factor with exponent given by the product of two numbers. One being this ideal counting function, and the other one the valuation of the special prime plus 1. And now, okay, maybe if you've never seen this before, you're not too impressed by this because, okay, you have a complicated quantity here and a very complicated formula on the other side. But really, I want to stress that this is an unreasonably simple formula. By means of an example, so I take two negative discriminants, -7 and -19, and I can write down an elliptic curve with Cm with these discriminants, and I have some J invariants which I have factored for you, or nice and smooth numbers. And now I will just compute the formula for you.
So those are actually special cases, right? Because you should think of J of E7 as J of E7 minus J.
That's right, yeah, because 0 is also a
Zero.
singular modular. Yeah, that's right. That's exactly right. But I will do it for these two. But that's a good observation indeed. But yeah, so I like this maybe slightly abstract looking index set of elements in a different totally positive trace 1. It's a very complicated way of saying that if I multiply by square root of d, I get an element of the norm x plus square d over 2, where x squared is just bounded by d itself. It's like the totally positivity condition coming in. And now the formula required me to like work out special primes. So let's just sort of see which primes occur in these numbers, but just computing their norm, and maybe this number is familiar to some people, and I record their special prime. So for example, 3 is inert in L over F, like a prime's above 3, but like 11 splits. So 3 here's a special prime, evaluation is 1, and because this 11 splits, I can write this ideal as a norm of 2 different ways. And I get this 2 here. And I sort of do this for each of these, 6 numbers. It's not even that many. Like in the 7, for example, it's split, so I get this norm twice. And here, this valuation of the special prime is a little bit bigger, and I get a 2 here, and I can just get once otherwise. So I can make this table in just a minute if I'm good at arithmetic. And then formula by Gross and Zagier, it says, okay, just take the difference between these numbers, which is 881,361, and somehow I can read off the prime factorization of this number from this table, which is, I mean, a bit of a magical thing if you've never seen this before, but it's true. Namely, this table predicts that we should have 1 times 1 is 1 factor of 13, 1 times 1 is 1 factor of 31, and 1 times 2 plus 2 times 1 plus 1 times 2 plus 1 times 1 is 7 factors of 3. And those of you who can, compute quite quickly might enjoy verifying that that's indeed exactly right. So there's something very special going on here. And Gross and Zagier, they proved this, and they each gave their own proof. Gross, he proved this roughly by just looking at the prime factorization of both sides of the equation. He just counted the primes on both sides and observed that it was the same. So the result had to be true. But Zagier, he did it in a very different way. He didn't look at prime factorizations. What he did is he just got an equality of these 2 numbers on the nose. And the way he did it can roughly be described as follows. He rewrote the theorem in the following way. So this very long single sum that I had in the theorem can be expressed a bit more concisely by introducing the second one. And now this looks a lot like the diagonal restriction of parallel weight K Hilbert-Eisenstein series, which has the following Fourier expansion, some constant term. But these higher Fourier coefficients of this modular form, they have the same index set, the same sum, and the chi in the norm, like everything seems to match up, except for the fact that here I get this logarithm, and here I get sort of the exponent of this norm. So it's not quite the same, but it feels like maybe we want to take a derivative with respect to k, so then the logarithm drops out, and then I plug in k equals 1 again, and then I sort of get this formula sort of from this Eisenstein series. But of course, k is an integer here, so I can't take a derivative, but it's still the idea of what you want to do. And that sort of leads to this one-line proof of this by Zagier, which is I take the diagonal restriction of some family now with a complex, like in a continuous parameter s. I take a derivative, I restrict it, I evaluate it s equals 0, then I get some kind of complicated object. But if I apply something called a holomorphic projection to it, I actually just get something of weight 2 of level 1, and it's holomorphic. So it has to be in this space, but we know that it's 0. So we've just computed 0 in the most complicated way imaginable. And why does it give us anything? Well, if you sort of look at the Fourier coefficients of just doing all of these steps, you don't get 0, at least not obviously. It sort of splits into 2 parts. Sort of by construction, one part will be this formula, but there's a conceptual way using Green's functions to also convince yourself that another contribution should come from exactly this number. And because you've constructed 0, you have these 2 parts have to be equal. So that's how Zagier did it. And I want to use Zagier's ideas to prove a generalization of this formula to you during this talk. So how do we go about generalizing this? Well, I want to change the setting a little bit by just going to a very easy class of Shimura curves. So no level structure. I just take an indefinite quaternion algebra. I take instead of it a maximal order. And then I choose the splitting, and I make it act on the upper half plane, and I can form this quotient, and that's a Shimura curve. It's an algebraic curve over Q, much like if you take, let B be M2 of Q, you just get the modular curve on which a J function lives, but now I get a different curve. But the difference with the modular curve case is that this one isn't always of genus 0, but it sometimes is, if you're lucky. So let's pretend we're lucky, and we just restrict ourselves to these 3 cases. If n is 6, 10, or 22, then the Shimura curve is of genus 0, and I can do two things. First, I write n as the product of two primes p and q, which happens to be possible. And the second thing I do is I will just choose a generator of the function field, which I apparently can do. But this choice is not unique, it's not canonical. So we'll have to be a bit careful with that. So, okay, next on our quest to try and generalize the theorem by Gross and Zagier is to evaluate these functions at CM points. So what is a CM point in the setting? It turns out the way you define you embed your maximal orders in your CM fields into the quaternion algebra, and they actually have unique fixed points in the upper half plane through the action of the quaternion algebra. And these are the right way to define CM points, but we can only define these embeddings as soon as P and Q are both inert in these two fields. So that's something we will assume. And now what we want to study is sort of the norm of the difference between these two numbers. But of course, this problem is still a bit ill-defined. By some version of Shimura reciprocity, at least we know that if we choose Jn appropriately, these numbers will be algebraic. But Jn is still not uniquely defined. So this problem isn't very clear yet. But before I address that, I want to change the way we view this problem by moving away from the complex numbers and in fact going to the p-adics. And the way we do that is we observe that this curve xn actually has bad reduction at p. And it allows, is following very beautiful p-adic uniformization, in which we take a different quaternion algebra, it sort of neighbors the one we started with. This one is only ramified at one of the two primes dividing n, let's say q. And then what I do is I take inside of it a maximal order, and I invert p, and then I take the units of norm 1. So then I get this different group, and this one, it's split at p, so I can make it act on the p-adic upper half plane, and I get another quotient, which at first sight doesn't seem related to the previous one at all, but sort of the miracle theorem by Sretnik and Drinfeld, in a sense, is that over Cp, this space is actually isomorphic to the Shimura curve that we started with. And I won't explain the proof, but it's very, very useful for us because one of the big advantages of this p-adic perspective is that this sort of mysterious Jn function that we had on the previous slide, we can try to see what it corresponds to on this p-adic quotient. And because on this p-adic quotient, these functions that we're looking at actually become very explicit. And we construct many functions on this quotient just by taking 2 points in the p-adic upper half plane, and we can just define this infinite products over all the elements of the group that we sort of divide out by. And we get this p-adic product, which converges now p-adically. Like over the complex numbers, you can't do this because it doesn't converge, but p-adically you can. And you get these things called theta functions. And in general, they transform with some kind of automorphy factor, but in a genus 0 case, they actually descend to honest, rigid analytic meromorphic functions on this quotient. And but sort of by construction, their divisors is just W1 minus W2. Question.
There is no sign condition, no Archimedean condition to make the thing converge here. It's
no, it's just that this. Yeah. Right. So if we abuse notation a little bit and suppress the rather intricate isomorphism provided by Sretnik and Drinfeld, we can sort of say that this theta function up to some constant must equal this quotient of this Jn function just by comparing divisors on this genus 0 curve. But okay, if we want to sort of transpose our problem of the CM values of this to this, it's still a bit unfortunate that we have this unknown constant that sort of messes everything up. And we can actually work around this in a very silly way. We just take this equality, we plug it in 2 different values of z, and then we just divide out. So the constant drops out, and we can get something completely well-defined. And what better choice as base points is a CM point and its Galois conjugate CM point, which now exists in the p-adic upper half plane. And what better points to evaluate at is another CM point with a different discriminant, tau2, and the other Galois conjugate CM point. So I get this sort of cross ratio of these Jn values, of the CM values of this Jn function, and completely without making any choices of what this function is, it must equal this p-adic infinite product of cross ratios of these CM points. And so this is a completely well-defined problem, and this is a quantity that I would like to study, because the nice thing about this, it's completely explicit. You can just write some magma code evaluate this to some high arbitrary p-adic position so to recognize it as an algebraic number in the right field. And well, people have done this, and you can even make conjectures about its values. So to state a conjecture, I need a tiny observation that because these primes p and q, to get these CM points, I had to assume they were inert in my Quaternion algebra. They had to be, they had to be inert in these two fields. So they must split in this field F. So I get 4 ideals of norm n. And I just take one Galois orbit, I assign it the sign +1, the other one -1, doesn't really matter how I do it. Because then the following was conjectured by Sophia Gianpietro and Henri d'Armont, was that this expression, sort of the norm, this number, this algebraic number that I've defined here, is up the sign given by this sort of gargantuan formula that barely fits on the slide. But knowing the result by Gross and Zagier, it's not quite as scary as it looks, because this first sum only has 4 terms, and it's just some signs, which sort of comes from the fact that now we have some cross ratios. So you get some things in the numerator and some things in the denominator. This index set here is exactly the same, and we still get a logarithm of the norm of special prime, and this exponent still splits into 2 parts, this ideal counter and this valuation of the special prime +1. The only difference is that everywhere I had to insert this ideal of norm A of norm n. And if I plug in A = 1, I recover beautifully exactly the result by Gross and Zagier. And it's this theorem that I would like to explain to you how I prove this. And the idea of the proof is as follows. We like Zagier's proof, so we want to mimic this, but in a p-adic way. But and we want to sort of use the theory of p-adic modular forms. So, but before we can use this Einstein series E1 chi as a p-adic modular form, we have to choose a p-stabilization. And in our case, these primes are above p are in fact regular, and we choose the following p-stabilization. So these VPs, the level raising operators of these Hilbert modular forms. And I have 4 choices of the p-stabilization by choosing these signs. And very crucially, we choose the signs, we choose 2 different signs. And the result of that is that if you look at the values at the cusps, they actually cancel out. So I get like a p-adic cusp form from this p-stabilization of this this Eisenstein series. And we want a cusp form because we want to write down a family of modular forms passing through it, but not just any family, a cuspidal family. So the strategy is to look for some kind of cuspidal family of Hilbert modular forms that passes through this guy. We want to take its diagonal restriction. We want to sort of take the derivative of this family with respect to this parameter, and then apply sort of the p-adic analog of the holomorphic projection, which here is the ordinary projection. And the result, when all the dust is settled, is just some nice way too modular form of level gamma naught of n. And okay, if n is 6 or 10, this space is 0. So we have constructed 0. If n is 22, it's not quite 0, but we can still prove that we have made 0. So we sort of recover the same conclusion, and hopefully our theorem will follow from this procedure, just like the resultant singular moduli followed from this in Archimedean setting. And this mimics clearly Zagier's proof, as I explained, but this p-adic approach to this problem has also recently been exploited by d'Armont, Alice Pozzi, and Jan Vonk in their work on rigid meromorphic co-cycles in RM theory. But we do it in the CM setting. So it's cool to see that this approach seems to generalize to sort of both worlds in that sense. So that's very interesting. And one complication, by the way, I want to highlight here, that's a subtlety in my argument, is that if I write down this family the way I do it, the S = 0 specialization in fact does not vanish. And typically when you take a derivative of something and you expect the result to be meaningful, you want the specialization to vanish. So almost you would argue, okay, but then this is a completely meaningless object. But we're saved by choosing our family in a so-called anti-parallel weight direction. And the idea, so there's that sort of weight 1 minus s, 1 plus s, so that the weight of the diagonal restriction, which is sort of obtained by adding these 2 weights together, is constant. And when we have that, it doesn't matter too much that our specialization doesn't vanish, because we can always subtract a constant family. Then that family does have a vanishing specialization, and you expect the derivative to be meaningful, and then I can just add the constant family back. So this still makes sense. But this is a subtlety that we can only deform in sort of in this very specific weight direction.
Can you say what this E-ORD map does?
Yeah, I will actually give an explicit definition on the next slide. So yeah, the nice idea, like, so if we have the family, if you sort of trust me for a moment that I can give you this family, and it's described by some kind of Fourier coefficients, which for Hibble modular forms are indexed by totally positive elements of the field F, I can compute the diagonal restriction and this derivative just by grouping together these elements of fixed trace. Now you will see here I take a very specific ideal with which to take the diagonal restriction. I have to insert this ideal above Q for technical reasons, which is actually the cause of the non-vanishing of the specialization. But that's a technicality. And once you have these coefficients, then computing the ordinary projection of this just comes down to computing this p-adic limit of these Fourier coefficients when we just add more and more factors of p to the coefficients of our modular form. So that's how you can define the ordinary projection operator. So once I give you these Fourier coefficients, everyone in this room shall be able to complete the argument by just performing these two computations. Like it's not the difficult part. The hard part is coming up with this family, right? How do you write down a p-adic family of cusp forms? It's not clear how you would do it. And the strategy that's sort of been used in this setting is quite nice. You don't try to just write down randomly some kind of family of modular forms. You have no hope. But what you do is you look at the Galois representation associated with this Eisenstein series. And what we do is we deform this Galois representation, and then we show an R equals T theorem to prove that all these deformations that we look for, in fact, come from modular forms. And then once we've proved this R equals T theorem, for which there's like techniques available, we can then take our favorite deformation in the right weight direction and deduce from it back the Fourier coefficients, and we get the family of modular forms. So that is the strategy that we employ. So this is like a large part of my paper. I don't want to focus on it too much now. I think many people have already talked about it. I just want to conclude by giving you like a small flavor of how sort of how easy it is to really get on the nose this explicit sort of bizarre looking Gross and Zagier formula from a very simple deformation, sort of highlighting how this approach really sort of seems to get you the quickest way from some kind of deformation to this sort of bizarre looking formula. By just taking sort of a toy example, I take the following deformation of this representation, which in the paper I have to take a bit more like of a refined deformation, because the deformation theory for like decomposable representations is a bit more difficult. So I rigidify it and have to take like a little bit more care. But let's just assume that this very simple deformation, where I just put like cyclotomic character infinitesimally on the diagonal, is in fact modular. So it comes from some kind of modular form, which means some kind of morphism from the Hecke algebra to the ring of dual numbers. I just recall very quickly that this Hecke algebra is generated by operators TL and diamond L for all primes co-primed P. But at P, because this is like a p-adic theory, the theory is very subtle, and we actually have operators U pi, which are very sensitive to the uniformizer. So I can't just work with ideals. But okay. Let's just focus on what happens away from P, because you can just, well, what is the image of TL? I just take the trace of Frobenius, and I get two cases. Either it's 2 or it's this infinitesimal part, and I get the image of the diamond operator by taking the determinant. And once you have these two values, then we still have this beautiful recursion relation that we all know and love. It still holds in this case. And you can solve this recursion and get some kind of formula for these Hecke operators, and then so for any prime power, and then for any ideal, just sort of multiply some of these things together, as long as it's co-prime to P, I just get this very explicit formula. And this looks sort of messy, and I'm not sure what I'm getting at here, but I want to sort of convince you that secretly you're staring here at the explicit formula that Gross and Zagier proved. And I arrived at it in like 2 or 3 lines of computations. And why is that? Well, it turns out this sum, it's secretly not really a sum, because of this factor 1 minus chi L to the n, the only primes that contribute to the sum at all must be the special primes. And if I have more than one special prime, then sort of this quotient ideal will still have a special prime. And what I said in the beginning, having a special prime means your rho value is 0. That means that this guy is also 0. So the only way I can get any non-zero contribution from this disgusting looking sum is if I only have one special prime, exactly as Gross and Zagier had in their formula. And then I just get this logarithm of the norm of the special prime. This n plus 1 becomes this valuation, and this rho becomes this rho. So if you just get it on the nose. So it's really, to me, it feels like they're really a very correct way of arriving at this result, just because it comes so easily. But of course, I haven't told you what happens at P. Like, this is all away from P. The theory is much more sensitive at P. So that's something we would still have to compute. And conceptually, you would expect it to come from some kind of p-adic height pairing on the Shimura curve, or it's Jacobian. Just like in Gross and Zagier, you got sort of this result that related the result of their operation to like a height pairing of Heegner divisors. And there is, in fact, a paper by Werner which sort of shows that this quotient of p-adic theta functions, it's related to like a Schneider height on the Jacobian of certain like Mumford curves. But you don't even need to know this conceptual justification. You can just perform the computation, see what the contribution at P is. If you go through all the steps, right, the derivative, the diagonal restriction, the ordinary projection, and what you get is exactly this. And because I've constructed 0, right, that was the core idea, I will get that this object, which is sort of the contribution at P, equals this formula, which is the contribution away from P. And yeah, so yeah, I think it's a very nice proof, and I would like to see how far I can push it to sort of refine these ideas and to apply it in more different contexts. If you want to learn more, you can maybe take a look at my paper. It's on archive. But for now, I think I would just like to thank you very much for your attention.